before the universe existed, before the first star ignited, before the first atom formed, before time itself began to tick. What was there? It's a question so strange that it almost feels impossible to even imagine. Because when we try to picture the beginning of everything, our minds instinctively reach for something familiar. A dark, empty space, a silent void, a blank, black canvas stretching forever. But according to modern physics, that picture is already wrong. Because even empty space is still something. So what if the truth is far stranger? What if the universe didn't begin inside empty space, but instead created space itself? And if that's the case, then we are left with one of the most profound mysteries humans have ever asked. How could nothing exist before the Big Bang? Or perhaps an even deeper question: was there ever truly nothing at all? Tonight, we're going to explore one of the biggest puzzles in modern science, the origin of the universe itself. We'll look at what the Big Bang really was, why scientists say time may have started at that moment, how quantum physics suggests that something might emerge from nothing, and why some theories suggest our universe may not have been the beginning at all. By the end of this journey, you may realize that the question of nothing is far more mysterious than it first appears, and that the universe might be far stranger than we ever imagined. So let's begin at the moment everything started. The beginning of the universe. About 13.8 billion years ago, something extraordinary happened. In an instant that scientists call the Big Bang, the universe burst into existence, not as an explosion in space, but as the creation and expansion of space itself. This distinction is incredibly important. When people hear the phrase Big Bang, they often imagine something like a bomb exploding in a dark, empty void, matter flying outward into pre-existing space. But that isn't what happened. Instead, the Big Bang was the moment when space, time, matter, and energy all began expanding together. Before this event, there wasn't empty space waiting to be filled. There wasn't darkness. There wasn't silence. Because even those require space and time to exist. And according to our current understanding of physics, space and time themselves began with the Big Bang. Imagine inflating a balloon. As you blow air into it, the surface of the balloon expands in all directions. If tiny dots were drawn across the surface, each dot would move away from the others as the balloon grew. From the perspective of any single dot, it would look like every other dot was moving away from it. In many ways, our universe behaves in a similar way. Galaxies are not flying outward through space like shrapnel from an explosion. Instead, space itself is stretching, carrying galaxies along with it. And the evidence for this expansion is everywhere. In the 1920s, astronomer Edwin Hubble discovered something remarkable. When he looked at distant galaxies through powerful telescopes, he noticed that their light was shifted toward the red end of the spectrum. This phenomenon, known as redshift, occurs when light waves are stretched, and the farther away a galaxy was, the more its light was stretched, which meant something incredible. The universe was expanding. Galaxies were moving farther apart over time. And if the universe is expanding today, then logically, it must have been smaller in the past. If we rewind the cosmic clock far enough, everything in the universe would eventually converge to a point of unimaginable density and temperature. A state scientists sometimes describe as a cosmic singularity. At that moment, the entire observable universe may have been compressed into something smaller than a single atom. Then suddenly, it began expanding. In the first fractions of a second, the universe expanded at an incredible rate in a period known as cosmic inflation. Space stretched faster than the speed of light. Tiny quantum fluctuations, microscopic variations in energy, were magnified across enormous scales. Over time, these tiny variations would become the seeds that eventually formed galaxies, stars, and planets. In other words, the structure of the universe we see today may have originated from tiny fluctuations smaller than an atom. Within the first few minutes after the Big Bang, the universe cooled enough for the first simple atomic nuclei to form: hydrogen, helium, and small traces of lithium. Hundreds of thousands of years later, electrons combined with these nuclei to form the first neutral atoms. At this point, light could finally travel freely through space. That ancient light is still detectable today. It fills the entire universe as a faint glow, known as the cosmic microwave background. In many ways, it's the oldest photograph of the universe, a snapshot of the cosmos when it was only about 380,000 years old. And it confirms something astonishing. The universe truly did begin in a hot, dense state. But this discovery leads us to a much deeper mystery. Because if the Big Bang marks the beginning of the universe as we know it, then what came before it? Was there a universe before ours? Was there an empty void? Or was there truly nothing? The word nothing sounds simple. But in physics, it becomes incredibly complicated. When most people imagine nothing, they picture an empty space, a dark vacuum with absolutely nothing inside it. No stars, no planets, no atoms, just pure emptiness. But even this kind of emptiness is not truly nothing, because a vacuum still contains space. It still has physical properties. And according to quantum physics, even the emptiest vacuum imaginable is filled with activity. Particles constantly appear and disappear in tiny bursts of energy known as quantum fluctuations. This means that even empty space is actually a dynamic and restless environment. In other words, what we call empty space is actually full of invisible energy. So if even the vacuum of space isn't truly nothing, then what would real nothing look like? True nothing would mean no matter, no energy, no space, no time, no laws of physics, no dimensions, absolutely nothing at all. But here's where things become incredibly strange, because once we remove space and time from the equation, the idea of before the Big Bang might stop making sense entirely. And to understand why, we need to talk about time itself. When we ask what happened before the Big Bang, we are assuming something very natural. We assume that time existed. After all, everything in our everyday lives happens inside time. Events follow one another in a sequence. A cause comes before an effect. Yesterday leads to today, and today leads to tomorrow. So when we imagine the Big Bang, our minds naturally place it somewhere along that timeline. We picture an endless stretch of time. And then suddenly, the Big Bang appears at some point along it. But modern physics suggests something much stranger. What if the Big Bang wasn't just the beginning of the universe? What if it was the beginning of time itself? To understand this idea, we need to take a brief journey into one of the most important discoveries in physics, Einstein's theory of relativity. Before Albert Einstein, scientists thought of space and time as completely separate things. Space was the stage where the universe existed. Time was the clock that measured how events unfolded. But Einstein discovered that space and time are actually woven together into a single structure known as space-time. Space-time is the fabric of the universe. Every planet, every star, every galaxy exists within this four-dimensional structure. 3 dimensions of space and 1 dimension of time. And here's the key idea. Space and time are not fixed and unchanging. They can stretch, they can bend, they can even distort. Massive objects like stars and black holes curve space-time around them, which is what we experience as gravity. But if space-time can bend and stretch, then it also means space-time can expand. And according to our best cosmological models, the expansion of the universe means that space-time itself has been stretching since the Big Bang, which leads to an extraordinary conclusion. If we follow this expansion backward in time, the universe becomes smaller and denser. Galaxies move closer together. Temperatures rise. Energy becomes increasingly concentrated, until eventually we reach a point where our equations break down entirely. A moment where density becomes infinite. A moment where space-time itself collapses to a single point. This hypothetical point is called a singularity, and according to many interpretations of the Big Bang model, this singularity represents the beginning of space-time itself. If space-time began at that moment, then time also began there. And if time began there, then asking what happened before the Big Bang might be like asking a very strange question. It might be like asking, what is north of the North Pole? At first, the question sounds meaningful. But when you examine it carefully, you realize something interesting. North only exists on Earth's surface. Once you reach the North Pole, there is no direction further north. The concept stops making sense. Some physicists believe the Big Bang may represent a similar boundary, a limit beyond which the concept of before simply does not apply. Stephen Hawking once explained this idea with a beautiful analogy. He suggested that the beginning of the universe might be like the South Pole of time. Just as there is no location south of the South Pole, there may be no moment earlier than the beginning of time. Time simply starts there. But this idea raises an uncomfortable thought. If time itself began with the Big Bang, then the universe didn't emerge at a moment in time. Instead, the Big Bang may be the moment when time itself came into existence. In other words, the universe didn't appear inside time. Time appeared with the universe. And that means the phrase, before the Big Bang, might not refer to anything real at all. Because before requires time to exist. And if time didn't exist yet, then there may have been no before. But physics doesn't end there. Because when scientists look closer at the earliest possible moments of the universe, something else begins to appear. Something that seems to challenge our everyday understanding of reality. Something strange, something unpredictable. The world of quantum physics. And in that world, the boundary between something and nothing becomes far more mysterious than anyone ever expected. At first glance, the idea sounds impossible. How could something come from nothing? In everyday experience, this never happens. A tree grows from a seed. A building is constructed from materials. A star forms from clouds of gas and dust. Everything seems to require something else to exist first. Cause leads to effect. This principle feels so fundamental that it almost seems like a law of nature. But when physicists began exploring the microscopic world of quantum mechanics, they discovered something deeply surprising. At the smallest scales of reality, the universe does not behave the way our everyday intuition expects. In fact, the quantum world appears to be filled with spontaneous events. Particles popping into existence, energy fluctuations appearing from nowhere, reality itself flickering with constant activity. To understand this strange behavior, we need to talk about what physicists call the quantum vacuum. Earlier, we talked about how empty space is not truly empty. Even the most perfect vacuum possible still contains something called quantum fields. These fields exist everywhere in space, and particles are simply tiny excitations within these fields. You can imagine a quantum field like the surface of an ocean. Most of the time, the water appears calm, but occasionally, waves ripple across the surface. Particles are like those waves. They are temporary disturbances in the underlying fields of the universe. Now here's where things get interesting. Even when no particles are present, the quantum fields themselves cannot remain perfectly still. According to the Heisenberg uncertainty principle, certain properties of the universe cannot be precisely fixed at the same time. One of those properties involves energy and time. the uncertainty principle allows tiny amounts of energy to briefly appear, as long as they disappear quickly enough. This leads to the creation of what physicists call virtual particles. Pairs of particles and antiparticles that spontaneously appear out of the vacuum. They exist for only a fraction of a second before annihilating each other and vanishing again. These events happen constantly, even in the emptiest regions of space. The vacuum is not silent. It is alive with fleeting bursts of activity. Particles appearing, particles disappearing, energy fluctuating, reality constantly bubbling beneath the surface. So in a strange way, the universe already demonstrates that something can briefly emerge from what appears to be nothing. But remember something important. The quantum vacuum is still not true. Nothing. It still contains physical laws. It still contains quantum fields. It still exists within space and time. True nothing, absolute nothing, would mean the absence of everything. No fields, no energy, no space, no time, no physical laws. And that leads us to an even deeper mystery. Because if the universe came from nothing, where did the laws of physics come from? Why do quantum fields exist? Why do particles behave according to mathematical rules? Why is there a universe at all? Some scientists believe the answer might lie in the strange nature of quantum cosmology. Others believe our universe may be only one of many. And some theories suggest that the Big Bang itself might not have been the beginning. Instead, it might have been a transition, a transformation from something that existed before. In the next part of our journey, we'll explore some of the most fascinating ideas scientists have proposed. Ideas that attempt to answer one of the biggest mysteries of all. What, if anything, existed before the Big Bang? And the possibilities might be far more extraordinary than we ever imagined. So far, we've explored one possibility, the idea that the Big Bang may have been the beginning of time itself. If that's true, then asking what came before the Big Bang might simply be the wrong question. But not all scientists are convinced that the Big Bang was the true beginning. Some physicists believe something else may have happened instead. What if the Big Bang was not the birth of the universe, but the rebirth of it? This idea is known as the Big Bounce theory, and it suggests something fascinating. Before our universe began expanding, there may have been another universe that was collapsing. To understand this concept, imagine watching a movie of the universe playing forward. Galaxies move farther apart. Space continues expanding. Stars form and burn. Cosmic structures grow larger over billions of years. Now imagine running that movie backwards. Galaxies move closer together. The universe becomes denser and hotter. Eventually, everything compresses into an extremely small and incredibly dense state. This reverse scenario resembles what scientists describe as the Big Bang. But the Big Bounce theory proposes something different. Instead of collapsing into a singularity, a point of infinite density, the universe might reach a maximum compression and then bounce back outward, just like a compressed spring suddenly expanding again. In this view, the Big Bang was not the absolute beginning. It was simply the moment when a previous, collapsing universe reversed direction and began expanding again. A cosmic rebound. A bounce. This idea arises from attempts to combine two of the most important theories in physics: general relativity, which describes gravity and the behavior of massive objects, and quantum mechanics, which describes the behavior of the smallest particles in the universe. General relativity predicts that if enough matter collapses inward, gravity becomes infinitely strong, producing a singularity. But many physicists suspect that singularities may not actually exist in nature. Instead, they may represent a limitation of our equations. At extremely small scales, near the beginning of the universe, quantum effects become incredibly important. and quantum physics may prevent the universe from collapsing into a true singularity. Some versions of this idea come from a theory known as loop quantum gravity. In this framework, space itself may not be continuous. Instead, it may be made of tiny, discrete units, almost like pixels in a digital image. When the universe becomes extremely compressed, these quantum structures may create a kind of repulsive pressure that prevents infinite collapse. Instead of reaching a singularity, the universe bounces. If this theory is correct, then our universe might be only the latest cycle in a long chain of universes, each one expanding, eventually slowing, then collapsing, and finally bouncing into the next. A never-ending rhythm of cosmic expansion and contraction. In this picture, the universe may have existed forever, not as a single continuous expansion, but as an endless series of cycles, each universe giving birth to the next. But here's where things get even more fascinating. If a previous universe existed before ours, could traces of it still exist today? Some physicists have suggested that patterns in the cosmic microwave background, the faint radiation left over from the early universe, might contain subtle signatures from a previous cosmic cycle. Tiny irregularities in the distribution of energy, faint echoes from a universe that existed before our own. So far, the evidence remains uncertain. The patterns scientists observe can often be explained by simpler models of cosmic inflation. But the possibility remains open. And if it's true, it would completely transform our understanding of the universe. Because it would mean that our universe was not the beginning of everything. Instead, it would be one moment in an endless cosmic sequence, a universe born from the ashes of another. But the Big Bounce is not the only idea scientists have proposed. Some theories suggest something even more mind-bending. Instead of one universe replacing another, there may be countless universes being created constantly, a vast cosmic landscape where new universes are born all the time. This idea is known as eternal inflation, and it may suggest that our universe is just one tiny bubble in an infinite cosmic ocean. In the early moments after the Big Bang, something extraordinary happened. The universe expanded incredibly fast, much faster than the speed of light. This period is known as cosmic inflation. During inflation, space itself expanded at a staggering rate. In a fraction of a second, the universe may have grown from subatomic size to something far larger than a galaxy. This rapid expansion helps explain several mysteries about the universe. For example, it explains why the universe appears so smooth and uniform on large scales, and why distant regions of space share nearly identical temperatures. But inflation may not have been a one-time event. Some physicists believe inflation might actually never stop completely. In this model, inflation continues forever in some regions of space, while in other regions, it slows down and forms universes like ours. To visualize this, imagine a pot of boiling water. Bubbles constantly form and expand within the water. Each bubble represents a region where inflation has ended and a universe begins to evolve. Meanwhile, the surrounding space continues inflating, producing new bubbles again and again. In this picture, our universe would be just one bubble among countless others. Each bubble universe might have its own physical laws, its own constants of nature, its own structure. Some universes might expand forever, others might collapse quickly. Some might contain stars and galaxies, others might remain empty and lifeless. In fact, there could be universes where gravity behaves differently, universes where atoms cannot form, universes where time flows in ways we can barely imagine. This concept is often called the multiverse, an enormous collection of universes existing beyond our observable horizon. If eternal inflation is correct, then our universe might not be special at all. Instead, it could be one tiny region in an unimaginably vast cosmic landscape. But here's the challenge. If these other universes exist beyond our observable region of space. We may never be able to see them. Light from those universes might never reach us. They could remain forever beyond our cosmic horizon, which raises a difficult question. If we can't observe them, how can we know whether they truly exist? This question touches on one of the deepest challenges in modern cosmology. Where does science end and speculation begin? Theories like eternal inflation are based on serious mathematical models. They emerge naturally from equations describing the early universe, but without observational evidence, they remain hypotheses, possibilities waiting for confirmation. And yet, the idea is powerful, because it offers a potential explanation for one of the most puzzling features of our universe, the apparent fine-tuning of the laws of physics. Why do the constants of nature have exactly the values needed for stars, galaxies, and life to exist? Why is gravity not slightly stronger? Why is the strength of electromagnetism not slightly weaker? If the constants of physics were even slightly different, the universe might be completely lifeless. Some scientists believe the multiverse could explain this mystery. If countless universes exist with different physical laws, then naturally some of them will happen to support life. We simply find ourselves in one of those universes. Not because it was designed that way, but because it's the only kind of universe where observers like us can exist. But even this explanation leaves us with another profound question. Where did the multiverse itself come from? Why do these cosmic laws exist at all? Why does reality exist instead of nothing? And when we push these questions far enough, we arrive at the edge of scientific understanding, a boundary where physics begins to blend with philosophy. In the next section, we'll explore what scientists still don't understand about the origin of the universe, and why the mystery of nothing may be one of the deepest puzzles humans will ever face. For most of human history, people believed the universe had always existed. Ancient philosophers imagined a cosmos without beginning and without end, an eternal system that simply continued forever. But when the Big Bang Theory emerged in the 20th century, it dramatically changed that picture. Suddenly, the universe appeared to have a starting point, a moment when everything began. Yet some scientists still wonder if the universe might actually be far older than the Big Bang suggests. Not through a single continuous expansion, but through an endless cycle of universes. This concept is known as the cyclic universe theory, and it proposes something remarkable. The universe may go through repeating phases of birth, expansion, collapse, and rebirth, again and again, forever. To imagine this, picture the universe like a giant breathing system. First, it expands outward for billions of years. Galaxies drift apart, stars form and burn. Cosmic structures grow larger and more complex. Eventually, however, gravity begins to slow the expansion. The outward motion weakens. The universe reaches its largest possible size, and then the process reverses. Galaxies begin drifting back toward each other. The universe slowly contracts. Temperatures rise. Density increases. Everything moves closer and closer together, until the entire cosmos collapses inward in a dramatic event sometimes called the Big Crunch. In this moment, all matter and energy would be compressed into an extremely dense state. And according to cyclic universe models, that collapse could trigger another expansion, a new Big Bang, a new universe. Another cosmic cycle begins. If this idea is correct, then the Big Bang we observe may simply be the latest beginning in an endless chain of cosmic rebirths, a universe born from the remnants of a previous one. But there's an important challenge with this idea. Our universe does not appear to be slowing down. In fact, observations show the opposite. The expansion of the universe is accelerating. In the late 1990s, astronomers studying distant supernova explosions made a surprising discovery. Galaxies were not merely drifting apart at a steady rate. They were moving apart faster and faster, Something was pushing the universe outward. This mysterious force is now known as dark energy. Dark energy appears to make up about 68% of the total energy in the universe, yet we still don't know exactly what it is. If dark energy continues to accelerate the expansion of space, then the universe may never collapse again. Instead of ending in a big crunch, it may expand forever, growing colder and emptier over time. Stars will eventually burn out. Galaxies will drift so far apart that they disappear beyond each other's horizons. In trillions of years, the universe could become a dark and silent place. A scenario sometimes called the heat death of the universe. Yet even here, the story may not be over. Some modern cyclic theories try to work around the expansion problem. One fascinating example comes from brain cosmology, a concept inspired by string theory. In this model, our universe may exist on a three-dimensional surface, called a brain, floating within a higher dimensional space. And there may be other brains nearby. Occasionally, these brains could collide. When they do, enormous energy would be released, enough to create something that looks very much like a Big Bang. Each collision would generate a new universe. Then the brains would drift apart again, until eventually colliding once more. In this view, the Big Bang was not the beginning. It was a collision between higher dimensional worlds, a spark igniting the birth of our universe. If this theory is correct, then the cosmos might exist in a grand repeating pattern that stretches far beyond our imagination. But no matter which model we examine, the big bounce, eternal inflation, cyclic universes, we keep encountering the same profound mystery. Why does reality exist at all? Why are there physical laws that allow universes to form? Why is there something rather than nothing? These questions lead us directly to the edge of scientific understanding. And at that edge, even our best theories begin to fade into uncertainty. Modern cosmology has revealed extraordinary things about the universe. We've measured the age of the cosmos, mapped the structure of galaxies across billions of light years, detected radiation from the earliest moments after the Big Bang. We've built powerful theories that describe gravity, particles, and the behavior of matter at incredible precision. And yet, when it comes to the ultimate origin of the universe, there are still enormous gaps in our knowledge. One of the biggest problems lies in the conflict between two pillars of modern physics. General relativity describes gravity and the large-scale structure of the universe. Quantum mechanics describes the behavior of particles at the smallest scales. Both theories are incredibly successful within their own domains. But when scientists try to combine them, especially when studying the earliest moments of the universe, the equations break down. The Big Bang sits precisely at this boundary. At extremely small scales and extremely high energies, gravity must behave according to quantum principles. But we do not yet have a complete theory of quantum gravity. Without that theory, we cannot fully understand what happened at the very beginning. The singularity predicted by classical equations may not actually exist. Instead, the universe might have emerged from some deeper quantum structure we don't yet understand. Some physicists believe the answer may lie in string theory. Others explore loop quantum gravity. Some propose entirely new frameworks for understanding space-time. But so far, none of these ideas have been confirmed experimentally, which means the earliest moment of the universe remains one of the greatest mysteries in science. And even deeper than that is the mystery of the laws themselves. Why do the laws of physics exist? Why do they have the specific mathematical structure that they do? Why is the universe governed by elegant equations rather than chaos? Some scientists suspect the laws of physics may be inevitable, the only possible set of rules that can exist. Others believe the laws themselves may vary across different universes within a multiverse. And some philosophers suggest that the question may not have a final answer at all, because the human mind evolved to understand survival, environment, and everyday experience, not necessarily the ultimate foundations of reality. It may be that some aspects of the universe lie permanently beyond our understanding, yet the search continues. Because curiosity is one of the defining traits of humanity, from ancient astronomers studying the stars, to modern scientists launching telescopes into deep space, we continue asking the same timeless question: where did everything come from? And perhaps even more mysterious, why does anything exist at all? In the final part of our journey, we'll reflect on what the mystery of nothing really means, and why this question may be one of the deepest ideas the human mind can ever explore. When scientists study the universe, they often look very far away. Because the farther we look into space, the farther we look back in time. Light from distant galaxies may take billions of years to reach us, meaning we see them as they existed long ago. But when we study the Big Bang, astronomers are doing something even more extraordinary. They are trying to understand events that happened within the first fraction of a second of the universe's existence. And this period was unlike anything we experience today. In the earliest instant after the Big Bang, the universe was unimaginably hot and dense. Temperatures may have reached trillions of degrees. Matter as we know it could not exist. Atoms had not formed. Even protons and neutrons had not yet appeared. Instead, the universe was filled with an intense sea of energy and elementary particles constantly colliding with each other. Physicists divide this earliest era into several stages. The very first moment, known as the Planck time, occurred about 10 to the power of minus 43 seconds after the Big Bang. That number is almost impossible to imagine. A decimal point followed by 42 zeros before the number 1. At this moment, the entire observable universe was smaller than a single atom. And the laws of physics, as we know them, break down completely. Gravity, electromagnetism, and nuclear forces may have been merged into a single unified force. But because we lack a full theory of quantum gravity, scientists cannot yet describe exactly what happened during this earliest instant. It is one of the greatest unknowns in physics. After the Planck time, the universe continued expanding and cooling extremely rapidly. Within a tiny fraction of a second, a dramatic event may have occurred, a phase known as cosmic inflation. During inflation, space expanded at an astonishing speed. In less than a trillionth of a second, the universe may have grown from subatomic size to something roughly the size of a grapefruit, and then it kept expanding. But inflation did something even more important. It took tiny quantum fluctuations, microscopic variations in energy, and stretched them across enormous cosmic distances. These tiny variations eventually became the seeds of galaxies. In other words, the reason galaxies exist today may trace back to tiny, random fluctuations that occurred when the universe was smaller than an atom, the stars in the sky, the galaxies stretching across the cosmos, even the atoms in your body. All of them may ultimately originate from those tiny quantum ripples in the earliest moments of existence. And yet, despite all we've learned about those early fractions of a second, one question still lingers. What created the conditions for the Big Bang itself? Why did the universe begin expanding at all? To approach that question, scientists sometimes explore an idea that sounds almost paradoxical: the possibility that the universe might have zero total energy. One of the most surprising ideas in modern cosmology is this: the entire universe might have required no net energy to exist. At first, this seems impossible. After all, the universe contains an enormous amount of energy. Every star burning in distant galaxies, every particle moving through space, all of that energy must come from somewhere. But physicists have discovered something fascinating about gravity. Gravity carries negative energy. To understand this, imagine lifting a heavy object. When you raise it higher, you increase its gravitational potential energy. But when the object falls, that energy is released. In a gravitational system, energy balances can become negative. Now, imagine the entire universe. All the matter and radiation within it contribute positive energy. But the gravitational attraction between all that matter contributes negative energy. And according to some calculations, these two values may balance perfectly. Positive energy from matter and radiation, negative energy from gravity, total energy of the universe, 0. If this is true, something remarkable follows. The universe may not have required energy to come into existence. In a sense, the universe might have been able to create itself without violating the laws of physics. Physicist Edward Tryon proposed this idea in the 1970s. He suggested that the universe might have originated as a quantum fluctuation of the vacuum. Just as tiny particles can appear and disappear in empty space, perhaps an entire universe could emerge from a similar fluctuation. At first, this idea sounds absurd, but quantum physics allows strange events to occur, especially on extremely small scales. Normally, these fluctuations disappear almost instantly. But if the newborn universe began expanding rapidly through cosmic inflation, it could grow large enough to become stable. Once expansion began, the universe would continue evolving according to the laws of physics. Stars would form, galaxies would appear, planets would emerge, and eventually, observers like us might arise within it. In this view, the universe could be something like a cosmic free lunch, a reality that emerged naturally from the quantum properties of space itself. But even this explanation leaves a deeper mystery. Where did the quantum vacuum come from? Why do the laws of quantum physics exist? Why is there a framework capable of producing universes at all? Each time we answer one question, a deeper one appears. And that's what makes the origin of the universe such a fascinating puzzle. When scientists examine the laws of physics, they often notice something remarkable. The universe appears to be extremely finely tuned. Many fundamental constants of nature have very precise values. If these values were even slightly different, the universe might look completely different. Consider gravity. If gravity were slightly stronger, stars would burn much faster and collapse quickly. If gravity were slightly weaker, stars might never form at all. Now consider the strength of electromagnetism. If it were slightly stronger or weaker, atoms might not hold together properly. Chemistry, the foundation of life, would not exist. Even the mass of elementary particles plays a critical role. Change those masses slightly, and stable matter might become impossible. When physicists study these constants, they often realize something striking. The universe seems to sit within a very narrow range of conditions that allow complex structures to exist. Stars, planets, molecules, life. Why does the universe have exactly these values? One explanation is known as the anthropic principle. The anthropic principle suggests that we observe these particular conditions because only universes with these properties can support observers. If many universes exist, each with different physical constants, then most of them might be lifeless. But in a small fraction of them, the conditions might allow galaxies, stars, and life to emerge. We happen to live in one of those rare universes, not because it was specially designed for life, but because only in such universes could beings like us exist to ask the question. To visualize this idea, imagine a cosmic lottery with trillions of possible universes. Each universe has different values for gravity, particle masses, and physical laws. Most of those universes might collapse instantly or remain empty forever. But a tiny percentage could support complex structures. And it's inside one of those rare universes that observers emerge. However, not all scientists are satisfied with this explanation. Some argue that the anthropic principle explains why we observe a life-friendly universe. But it does not explain why the universe exists at all. Others worry that if the multiverse contains infinitely many universes, it becomes difficult to test scientifically, because we may never observe those other universes directly. Still, the anthropic principle remains one of the most intriguing ideas in cosmology. It suggests that our universe might be just one tiny possibility among countless others. A universe where the conditions happen to align in just the right way for complexity to arise. And within that complexity, life appeared. Consciousness emerged. And eventually, intelligent beings began asking questions about the origin of the cosmos, which leads us to one of the most astonishing aspects of this entire story. The fact that the universe has produced creatures capable of understanding the universe itself. When we talk about the universe, it's easy to imagine that we are referring to everything that exists. But in reality, the universe we can observe is only a small portion of the entire cosmos. This visible region is known as the observable universe. It represents the part of space from which light has had enough time to reach us since the Big Bang. Because the universe is about 13.8 billion years old, you might expect that we can see objects up to 13.8 billion light years away. But the true size of the observable universe is actually much larger than that. Due to the continuous expansion of space, distant galaxies have moved farther away while their light was traveling toward us. As a result, the observable universe today stretches roughly 93 billion light years across. Inside this vast cosmic sphere are hundreds of billions of galaxies. Each galaxy contains billions or even trillions of stars, and many of those stars likely have planets orbiting them. The scale of this region alone is almost impossible to comprehend. Yet even this enormous space is not the entire universe. Beyond the edge of the observable universe lies a region we can never directly see. Light from those areas has not had enough time to reach us. And because the universe continues expanding, some regions may never become visible to us at all. In fact, distant galaxies are moving away from us so quickly that their light will eventually never reach Earth. They will fade beyond our cosmic horizon. Imagine standing in the middle of a vast ocean surrounded by fog. You can only see as far as the fog allows. Beyond that boundary, the ocean continues, but you cannot observe it directly. The observable universe is similar. It's the region of reality, visible through the cosmic fog of time. But the universe itself may extend far beyond this boundary. Some cosmological models suggest that space might be infinite. If that's true, then beyond our observable universe, there could be countless other regions filled with galaxies similar to ours. Entire cosmic structures stretching endlessly through space. But because light from those regions will never reach us, they remain permanently hidden. This leads to a fascinating realization. Even if we mapped every galaxy we can see, even if we measured every star within our cosmic horizon, we would still only be observing a tiny fraction of the total universe. The rest may lie forever beyond our reach. This limitation shapes how we study the cosmos. Cosmologists must infer the properties of the entire universe based on the small portion we can observe. And so far, observations suggest something remarkable. On very large scales, the universe appears remarkably uniform. Galaxies are distributed fairly evenly across space. The cosmic microwave background shows almost identical temperatures in every direction. This large-scale uniformity suggests that the universe may follow the same physical laws everywhere. But there are still many unanswered questions. Is the universe truly infinite? Or is it finite but curved, wrapping around itself in some higher dimensional geometry? Could the universe eventually loop back on itself, like the surface of a sphere? Or does space stretch forever without end? Scientists continue searching for clues. Measurements of cosmic radiation, observations of distant galaxies, new telescopes capable of peering deeper into the universe than ever before. Each new discovery brings us closer to understanding the true shape and size of the cosmos. But even if we eventually answer those questions, a deeper mystery still remains. Because knowing the size of the universe does not tell us why it exists at all. And when we push that question to its limits, we begin exploring ideas that challenge our understanding of reality itself. One of the most surprising possibilities scientists and philosophers have discussed is this. What if the universe itself is not the ultimate level of reality? What if the cosmos we experience is part of something even larger? Something far beyond space and time as we know them. When scientists explore the deepest mysteries of existence, they sometimes encounter ideas that sound almost like science fiction. But these ideas often arise naturally from serious attempts to understand the laws of physics. One such idea is the possibility that the universe might not be the most fundamental level of reality. Instead, the cosmos we experience could be part of a deeper structure. One famous version of this concept is known as the simulation hypothesis. The idea is simple, yet deeply unsettling. If technology continues advancing, it might eventually become possible for intelligent civilizations to simulate entire universes inside powerful computers. Inside such a simulation, digital beings could exist. Those beings might perceive their simulated environment as reality. They might study the laws of physics within their universe. They might even develop science and philosophy to understand the nature of their existence. But from the outside perspective, their entire universe would simply be a simulation. If such simulations are possible, then a surprising possibility emerges. Our own universe could theoretically be one of those simulations. This idea was famously discussed by philosopher Nick Bostrom. He argued that if advanced civilizations can create large numbers of simulated universes, then statistically, it might become more likely that we live inside one of them. But it's important to emphasize something. There is currently no scientific evidence that our universe is a simulation. The idea remains speculative. However, it raises fascinating questions. If the universe were simulated, the laws of physics might resemble the rules of a computational system. Some physicists have even wondered whether certain properties of reality, such as discrete units of space and time, could resemble the pixels of a cosmic computation. But most scientists remain cautious about this idea, because a hypothesis must eventually produce testable predictions to become part of scientific theory. Without evidence or experiments, ideas like the simulation hypothesis remain philosophical possibilities rather than scientific conclusions. Still, exploring these ideas can help us think differently about the universe, because they remind us that our current understanding of reality may not be the final answer. Throughout history, humanity has repeatedly discovered that the universe is far stranger than we first imagined. Ancient civilizations believed Earth was the center of the cosmos. Later, we discovered Earth orbits the Sun. Then, we learned our Sun is just one star among billions in the Milky Way galaxy. And later still, we discovered that our galaxy is just one among hundreds of billions of galaxies. Each new discovery expanded the scale of reality. And there's no guarantee that our current understanding represents the final level. There may still be deeper layers of reality waiting to be discovered. Perhaps new theories of physics will eventually reveal structures beyond space-time itself. Perhaps the universe is part of a larger cosmic framework we cannot yet perceive. Or perhaps the ultimate nature of reality will always remain partially mysterious. But the search continues. Because every time we ask a question about the universe, we learn something new about existence itself. And sometimes the answers lead us to even bigger questions than the ones we started with. So far, we've spent most of our time looking backward, tracing the history of the cosmos all the way to the Big Bang. But if the universe had a beginning, then it must also have a future. And according to modern cosmology, the future of the universe may be just as fascinating and mysterious as its origin. To understand where the universe is heading, scientists study one of the most important discoveries in astronomy: the expansion of space. As we discussed earlier, galaxies are moving away from one another because space itself is just stretching. But for many years, scientists believed that gravity might eventually slow this expansion. Since gravity pulls matter together, it seemed possible that the universe might gradually lose momentum. Expansion would slow. Eventually, it might stop, and then gravity could pull everything back inward. This scenario would lead to a cosmic collapse known as the Big Crunch. In this model, the universe would eventually contract back into an incredibly dense state, perhaps triggering another Big Bang, perhaps beginning another cosmic cycle. But observations in the late 20th century revealed something unexpected. Instead of slowing down, the expansion of the universe is speeding up. In 1998, two independent teams of astronomers were studying distant exploding stars called Type 1a supernovae. These explosions act like cosmic measuring tools because they have nearly identical brightness. Scientists can use them to estimate distances across vast regions of space. When astronomers measured the light from these distant supernovae, they discovered something astonishing. The galaxies containing them were farther away than expected, which meant the expansion of the universe had been accelerating for billions of years. Something was pushing space apart. That mysterious force is now known as dark energy. Dark energy is one of the biggest puzzles in modern physics. We know it exists because we observe its effects, but we still don't know what it actually is. Some scientists think dark energy might be a property of space itself, a kind of energy embedded in the fabric of the universe. Others believe it may arise from new physics that we haven't yet discovered. Whatever its origin, dark energy now appears to dominate the universe. Roughly 68% of the total energy in the cosmos seems to be dark energy. About 27% is dark matter, another mysterious substance that we cannot see directly. And the ordinary matter that makes up stars, planets, and galaxies accounts for only about 5%. In other words, everything we can see in the universe represents just a tiny fraction of what actually exists. But if dark energy continues driving the expansion of space, the future of the universe may unfold in a very particular way. Over billions and trillions of years, galaxies will drift farther apart. Eventually, distant galaxies will move beyond the reach of our telescopes. Their light will never reach us again. The night sky will slowly grow emptier. In extremely distant future epochs, observers in our galaxy might not even know other galaxies ever existed. The universe will appear smaller and lonelier. Stars will continue forming for billions of years. But eventually, the gas that fuels star formation will run out. The last new stars will ignite. Then, slowly, they will fade. White dwarfs will cool. Neutron stars will drift through dark space. Black holes will dominate the remnants of galaxies. Over unimaginable timescales, trillions upon trillions of years, even black holes may evaporate through a process known as Hawking radiation. Gradually, the universe could approach a state of near-total darkness, a thin sea of particles drifting through vast empty space. This scenario is known as the heat death of the universe, a future where all usable energy has been exhausted. No stars, no galaxies, only a cold and silent cosmos slowly expanding forever. Yet even here, some physicists speculate that new universes might eventually emerge from quantum fluctuations. If the cosmos truly lasts forever, even incredibly unlikely events might eventually occur. Perhaps new Big Bangs could arise in the distant future. Perhaps entirely new universes could appear from the quantum vacuum. The cycle of cosmic creation might continue in ways we do not yet fully understand. And this idea leads us back to one of the deepest mysteries we began with, the question of nothing. Because when we examine the universe closely, something very strange begins to emerge. True nothingness may not be possible at all. When people imagine nothing, they usually picture an empty void, a dark, silent space with absolutely nothing inside it. But as we've seen, even empty space isn't truly empty. Quantum fields fill the vacuum. Particles flicker into existence and disappear again. Energy fluctuations ripple through space. So physicists began asking a deeper question. What would true nothing actually mean? To have absolute nothing, we would need to remove everything. No particles, no energy, no space, no time, no physical laws, no mathematical structure, no dimensions, nothing at all. But once we imagine such a state, something curious happens. It becomes extremely difficult to describe. Because the moment we try to talk about it, we begin using concepts like space, time, and existence. And those concepts already imply something. Some physicists argue that true nothingness might actually be unstable. In quantum physics, empty states rarely remain perfectly empty. Tiny fluctuations naturally occur. And if a state of absolute nothing somehow existed, it might not remain that way. The laws of quantum mechanics might allow a tiny fluctuation to appear, a fluctuation that could expand, perhaps forming a universe. Physicist Lawrence Krauss famously argued that universes might arise naturally from quantum processes. According to this idea, the universe may not require an external cause. Instead, the laws of physics themselves might allow universes to spontaneously emerge. But this explanation still leaves a deeper question. Where did the laws of physics come from? Why do these laws exist rather than others? Or perhaps an even deeper mystery. Why are there laws at all? Some physicists propose that the laws of nature may be the only possible set of consistent mathematical rules. Others believe the laws might vary across different universes within a multiverse. Still, others suggest that the concept of nothing may simply be a misunderstanding. Perhaps reality cannot be reduced to absolute nothingness. Maybe existence is somehow inevitable. Or perhaps the universe is part of a deeper mathematical structure that necessarily exists. These ideas push science into philosophical territory, but they also highlight something important. The question of nothing is not just a scientific puzzle. It is a question about the nature of reality itself. And when we explore it, we begin to realize something extraordinary. The universe may not just be a collection of stars and galaxies. It may be a profound expression of existence itself, a reality where something exists instead of nothing. And within that reality, we find ourselves thinking, questioning, wondering. And that may be one of the most remarkable facts of all. The deeper we explore the origins of the universe, the more mysterious the question becomes. At first, it seems simple. What existed before the Big Bang? But as science pushes further back in time, we begin to realize that the question itself may not have a simple answer. The Big Bang may have marked the beginning of space and time. If that's true, then the idea of before might not even apply. Time itself may have started in that moment, meaning there was no earlier state waiting in the darkness. Yet modern physics also suggests strange possibilities. Quantum fluctuations hint that something might emerge from what appears to be nothing. Theories like the Big Bounce, eternal inflation, and the multiverse suggest that our universe might be only one part of a much larger cosmic story. And still, one mystery remains. Why does anything exist at all? Why are there laws of physics, space, and time rather than absolute nothingness? For now, science does not have a final answer. But the search continues. Because every discovery brings us closer to understanding the universe and our place within it. And perhaps the most astonishing fact of all is this. Out of the vast universe, something emerged that can look back and ask why it exists at all.